Now we'll continue on the mechanism of a reaction, and we'll discuss slightly different topic right now, which is processes on solid surface. What happens when you use a catalyst which is in solid phase? Now, in many cases, you know that this is a very important process. For example, when you have read about this reaction that ammonia production from nitrogen and hydrogen, so that is energetically less favorable. But if you use platinum, iron catalyst on platinum asbestos, so then the activation energy of this reaction is pretty much down, and then you see the reaction proceeding at some ambient temperature. Now, for this, this was a revolutionary discovery, because if you remember, ammonia is used in fertilizers, and nitrogen and hydrogen are just, you can actually get it in abundance, particularly nitrogen. And then in nature, plants or the bacteria residing in the roots of plants, they do this process of nitrogen fixation, and that's how the plants get nutrient. But if you want to produce ammonia, not only for fertilizers, but also in many industrial processes, the Haber found that just using this catalyst, the rate of the reaction increases by a whole lot. And then the question is how basically the iron works here. So that process we are going to discuss today. So we're going to basically develop a model that will describe the mechanism of this, not only this reaction, any surface reaction, and particularly will give you an example of surface catalysis. This is an example of surface catalysis, by the way. So they are actually use iron particles, and once you suppose you can actually do it on an iron surface where so this reaction is slow. The reason is this nitrogen-nitrogen bond is very difficult to break. And what happens on iron surface, these bonds can be easily broken, and you get free nitrogen atom adsorbed on the surface, and also you have free hydrogen atoms adsorbed on the surface, and then these hydrogen atoms and these nitrogen atoms react together to give you ammonia. And the process happens on the surface, iron surface itself, and once the ammonia forms on the surface, it comes out of the surface, and that's how the reaction happens. So iron actually acts as a catalyst. And one more point I want to emphasize here. So usually you do not use a plate of metal or piece of metal. The reason is, if you use, you can ask this question that if you take a piece of metal and then break it into many small pieces in the size of, say, some few tens to few hundreds of nanometers or slightly more, then you can easily show that the volume is fixed, but the surface will actually, the total surface area will increase, or you can say the surface to volume ratio will also increase. Since these are all surface processes, if you can actually use, say, 1 gram metal in this form versus 1 gram metal in this nanoparticle form, you will see that there's a huge enhancement in surface moment to break the piece of metal into small particles. That's why people use small, they use actually metallic powder or something like that, so that the surface area is increased. Now the process of a gas which attaches on the surface, this process is known as adsorption. Now it has a meaning why we are calling it adsorption, because you have a surface and the molecules are sitting on the surface. That's it. They are not penetrating the surface. If it penetrates a surface and goes inside means it goes into the bulk medium, then this process is known as absorption, and you already know that. We are talking about adsorption. Now the question is, why adsorption will occur? So it must be energetically favorable. So then you can ask this question, okay, fine, can we have energy diagram? In this case, it's a potential energy diagram describing this process of adsorption. So what I'm plotting here is basically energy, or the potential energy, and suppose this is the zero of energy, Now zero of energy is arbitrary. By zero of energy, I'm saying that this x-axis is the distance from the surface, for example. And when I'm saying that it is the molecule which will get adsorbed is far away from the surface, so it has no interaction with the surface. So that point I'm talking at to be zero of potential. Now suppose we are bringing the molecule towards the surface, meaning we are just moving in this direction. And then what will happen is that as it is brought closer, then the molecule, there will be an attractive interaction, and that's why the molecule will get attached to the surface. And this will be the nature of the potential. So you see that at some point, at some specific distance from the surface, the potential energy is minimum. And then what happens that again, if you want to bring the molecule, suppose this is the molecule and this is the surface, and if you want to bring it more closer together, then the electrons on the molecules and the surface, electrons on the surface, they start repelling each other, and then actually you will have a repulsive force. So there will be a best position or best equilibrium position where the energy will be minimized. Now this process where just suppose I am starting with a molecule which I'm calling as, say, AB molecule. So there is a bond between A and B. Suppose A and B are atoms, or they may be a fragment of a molecule, and this state is AB plus surface. It is basically AB and surfaces are far apart. Now when I reach here, so here AB is basically stuck on the surface. So this AB is stuck on the surface. So that is basically known as, it's physically stuck. There is no chemical change in this process. So that's why we call this as Physisorption. It is an adsorption, but it is a physical adsorption. Now you can think of a process just like I told that when nitrogen get adsorbed on iron surface, the N triple bond N breaks. So then you get the nitrogen atoms. So that is actually causing a dissociation. So that is a chemical process. Now you can think that I can also have a chemical process where the molecules get dissociated. So we'll have a similar curve. Now that curve will look like something like this. I'll just discuss in a minute why I'm drawing this curve like this. Let me just remove this. Now you see here, I'm calling this curve as chemisorption as opposed to physisorption, where just it was physically adsorbed. Now what happens here, if the molecules get dissociated, then I'm calling this curve as chemisorption. So far apart, these molecules will be A plus B plus surface. So look at the very intricate difference between the physisorption thing. When the molecule is far apart, it is a molecule AB, but the AB bond has not been broken and there is no interaction between the surface. And what I'm showing here, the chemisorption state, it is basically the molecules is dissociated, the AB bond has broken, and there is a surface, but there is no interaction between the atoms and the surface. So when that process happens, that interaction should be much stronger than this interaction. So this potential energy will be much, much deeper than the chemisorption state. Also, you see that this curve, the chemisorption curve, in the asymptotic regime in the sense that it has basically it has I mean much larger distance from the surface. In that regime, if I think that so the energy difference will be nothing but the AB molecule and the A plus B atoms, or it may be the fragments. So a bond has been broken, which means this will be, there will be some energy difference between the AB and AB, A plus B, and of course A plus B will be of higher energy because you have supplied energy to the system, and that's why the bond has broken. Or in the other way, other sense, if the bond is formed from A plus B to AB, then you will release some energy. So AB is always stabilized. That's why this curve lies at the bottom. what happens when nitrogen molecule approaches the surface? Initially, we have here, we basically start from here. And then, so initial step is physisorption. Always, actually, there is a physisorption that actually precedes or that happens before chemisorption. And then what happens, you cross this little barrier that is shown here, and you come to the chemisorption state. So this chemisorption state is nothing but A and B stuck on a surface. So as soon as it is chemisorbed, it is dissociated. So this is why sometimes we call it as dissociative chemisorption. So it's physisorption does not dissociate. It's just a physical attachment. It's a weak attachment. But chemisorption is a strong attachment where basically the metal is now forming a bond with the. So what is happening here? So I had an AB bond, and then you can draw it like this. So this is basically the state here, state 1 say, and then at state 2 where I am at the physisorb state. So you can argue that it basically looks like this. So I have AB, but I have a very weak interaction with the surface, and then what happens? It crosses a barrier, and when it crosses the barrier, near the barrier, the situation is like this. The AB bond is being broken, and the A to surface and B to surface bond is being formed. And finally, you will have the AB bond completely broken, and a new bond has been formed between the A and the surface and the B and the surface. And that's how the N triple bond N also breaks. But it involves multiple steps, because you have to first make the triple bond to double bond, then double bond to single bond, and then the single bond to no bond, something like that. So all these things are happening. So now suppose the AB molecule is chemisorbed, where actually it is dissociated. Now when it goes back, so it now goes back following this curve, meaning when it goes back, it actually goes back as a dissociated atom. So that can happen, that may not happen. If the interactions of these atoms with the surface is strong, it may not happen. But the point here is that you can actually cleverly use a surface, which in many cases is a metal surface, and bring a molecule and then dissociate it. And then if you heat it up, maybe you can actually weaken that metal to atomic bonds, and then you can actually dissociate it into atoms. However, you may not be able to do it in the gas phase, because you have to supply a lot of energy to break the bonds in the gas phase. But what happens is that there is a physisorption state, so it is weakly attached, and then there is a barrier. But this barrier, now you can see this barrier here, if I just magnify it, it is something like this physisorb state is going into the chemisorb state. So this is the minimum of the physisorb state, and there will be a minimum of the chemisorb state. So this barrier, which we'll discuss detail in later, is called an activation barrier. And that activation barrier is very small, and that's why the surface catalysis works. So there's a physisorption and there is a chemisorption, and prior to chemisorption there is a physisorption, and that's why it is already energy is lowered, and then you have a chemisorption. If you ask this question that if the physisorption did not happen, what will be the case? So the chemisorb state is something like this, and then there is suppose no physisorption, which means actually now the molecule starts from here in the asymptotic limit. Now it has to somehow come and cross this barrier, which is this. So it has to proceed through a path which is something like this, and then only it can do the chemisorb, then it can only dissociate. So now you see that there is a huge difference between physisorption followed by chemisorption and only dissociation by chemisorption. So that's why surface catalysis, that's the inherent way of thinking, intuitive way of thinking, why surface catalysis works. It only works by lowering the height of the barrier, and that is connected to the rate constant through Arrhenius equation that we'll be studying later. Now the question is, how will you model, develop a kinetic model to describe the mechanism of such processes? And the mechanism is very simple, and this mechanism was put forward by Erwin Langmuir. an American physical chemist who did a lot of work on surface science. So what Langmuir said is that suppose you have a gas which is A, and then you have a surface which is solid, and then there's a first equilibrium between the gas adsorbed on the solid. So this is now as if it is a solid state. So the gas A is attached to the solid, and then the forward rate we call it as a rate of absorption, and the reverse rate we call it as a rate of desorption. So D stands for desorption. It is opposite to adsorption. A is adsorption. Now there is a first equilibrium between them, and the question is how do you quantify this equilibrium. Now you cannot actually calculate the what Langmuir suggested is that suppose we have some available sites where the molecule can come and sit. So suppose these are molecules, these are floating in gas, and then the molecule will come and sit on the surface. So then you'll have a molecule stuck on the surface. So at any point of time you can think there will be some sites which are vacant or free and some sites which are occupied. So like this is occupied because no other molecule can sit on that, and here it is basically vacant site. So let us consider the fraction of this vacant site, fraction of free site or vacant site is, say, I'm calling as theta. And then also consider that the surface area is, just take a number, say, or a notation, let's call it as a sigma. Usually we use the sigma for surfaces. Now what Langmuir said, the rate of adsorption which is the forward process, will be nothing but, if I just call it as a VA, that will be nothing but proportional to how many sites are vacant. So instead of writing the theta as a vacant, I can write it as a fraction of sites occupied as theta. I mean, this is just a notation. So then the adsorption will be dependent on what fraction is available. So that fraction, since this is a fraction, it will be 1 minus theta. So that fraction is basically available. It will also, that fraction times the area will be the number of available sites, because we are using a fractional notation, and times it will also depend on the concentration of A, because you have more number of gas molecules here, of course the rate of adsorption will be more. It is as simple as that. And you'll have a rate constant associated with it. It is the forward rate constant. Similarly, the rate of desorption will also be equal to something like, it will be now dependent on theta, because theta is the rate of occupied sites, how many sites are occupied, into sigma. But it don't depend on the pressure of or concentration of the gas, because it doesn't matter, because it is just adsorbed on the surface and it is just going into the gas phase. But however, if you have more number of molecules in the gas, then there is a chance to go sit on the surface. But if it is already on the surface, so then it's a spontaneous process which is basically going into the bulk phase or the gas phase. So, and then associated here we also have a desorption rate, and at equilibrium at a fixed temperature, so the rate of adsorption and desorption will be same, and we can just equate these two equations, and you can see that the sigma thing gets cancelled. So you can readily solve it, and you can show it that I'll get 1 by theta is 1 plus, I'm just skipping this for the time being, some equilibrium constant, which I'm calling is at as K equilibrium. So you'll get a ratio of K adsorption by K desorption, that you can write it as that ratio as an equilibrium constant times the concentration of A. But usually do not use concentration, because it's a gas to solid surface adsorption. So instead of concentration, you write it in terms of the partial pressure or pressure. So if there are multiple species, then there will be partial pressure, otherwise it will be just pressure. So you just write it as a same equilibrium constant. It won't be the same equilibrium constant, because moment I write it in terms of pressure, then there will be other factors, like I have to divide by P0, the standard pressure, and convert the concentration into pressure. So then there will be some factor multiplied by the equilibrium constant, but that will also be another equilibrium constant. That I'm writing it as B, and then pressure of A. Now we can also write what is the value of theta. Now theta, you can just rearrange it. You will see that it will be B into PA divided by 1 plus B into PA. Now if you want to plot it, the adsorption, this is known as adsorption isotherm, because we said that we are doing this experiment at constant temperature. So if we plot this thing theta, the rate or the fraction of sites occupied versus the pressure of the gas, you will see that at low pressure I can actually ignore this term B into PA compared to 1. So it is linearly proportional to PA. So it will have something like this. And at a very high pressure, then this term will be very high compared to 1. So it will be BPA by BPA. So then actually fraction will saturate. So it will go like this, where basically this is a saturation point. Theta is a fraction, so it can maximum value of theta can be 1. So we see a curve which is very interesting, because we saw this curve in Michaelis-Menten equation. If you remember that when we were plotting the initial rate V0 versus initial substrate concentration, that also looked similar way. Now the physics is very similar, because if you think that in the Michaelis-Menten situation, what we had is that we had enzymes, and each enzyme had a particular site for substrate binding. So you can think that there will be some free enzyme, and there will be some enzymes which are already occupied, and in the Langmuir's language, and it is the same here also. There are sites. The sites are each site you can think of in one enzyme, and one molecule binds to one site only binds to one molecule, not to multiple molecules. That also we kind of are good, or in a model we basically that we put that constraint. And if you think in that way, then there is not much difference between the enzyme catalysis and this surface catalysis. Although enzyme catalysis is in a homogeneous catalysis, in the sense enzyme, substrate, and everything, the product is in the same phase. Here they are in different phase. So that's why you call it as a heterogeneous catalysis, this ammonia production from nitrogen and hydrogen, because there is a gas phase and there is a solid phase, which is the metal surface. So it's a two-phase system, and that's why we call it as a heterogeneous catalysis. Now the concept is very similar. That's why you're getting similar nature of the curve. Now one more thing. So this is known as a Langmuir adsorption isotherm. But in real life, what you see here, that once I have the, suppose these were the surface sites, I can just draw it like this. Suppose these are the surface sites, and when you have enough pressure, then the molecules are coming and sitting on that, and all sites are occupied, then you cannot have further molecule. So here actually what Langmuir adsorption isotherm says is that you stop at the monolayer formation. Monolayer in the sense that only one molecule layer, one molecule thick layer is there, not multiple molecules. But in reality what happens is that when you have particularly at low temperature, when you have this situation, then the other molecule can sit on this molecule, and other molecule can sit on this molecule, and then you can actually go from monolayer to what is known as multi-layer. And after a certain point, actually you cannot control this. Moment you increase the pressure, you'll see all the molecules are sitting on the surface, because that is what is known as condensation. So you have seen that if you take a metal surface at cold temperature and put it in a, say, or any surface in a say cloudy day, or when you have enough humidity in air, so you'll see that water vapor actually condenses on the surface. So condensation means actually you'll have multiple layer, because you can see the layer, so which means actually there are several atomic several molecule are sitting vertically, and that is basically shows the condensation. So attaching of one molecule is facilitating the attaching of multiple molecules. And then the curve will not look like this. After certain pressure, you'll see that this curve will just blow up. And for that, actually, we cannot explain from Langmuir adsorption isotherm. So this is known as Langmuir. Maybe we can draw it as a dotted line like this. Adsorption isotherm. And then this curve, there is a model for that. It is known as BET model, but we will not discuss it here, which actually discusses this multi-layer adsorption case. So Langmuir adsorption is limited to only those situations where it forms only monolayer, and it just stops at the monolayer formation, and no multi-layer formation is no multi-layer formation occurs further. Now, as I said, that this model I can use for catalysis, and by catalysis again I talk about heterogeneous catalysis. Now, instead of the nitrogen and hydrogen reaction producing ammonia, we'll talk about some interesting reaction where carbon dioxide, carbon monoxide, and oxygen both are gas, and in presence of a surface they form carbon dioxide. Now the question is, what is the mechanism of this reaction? Now two mechanisms were proposed, and so the first mechanism says that the first part of these two mechanisms is same. So you have carbon monoxide gas, which actually in presence of the surface is going to the carbon monoxide in the adsorbed state. This will be just like what we just developed through Langmuir mechanism. And then you have oxygen gas, which is also getting adsorbed, but this case it is a dissociative chemisorption. And then the first model, which is known as the Langmuir or Hinzelin model, it says the reaction happens between the adsorbed carbon monoxide and the adsorbed oxygen atom, and then you will have CO2. So this is basically the final step or the rate determining step. And the other model says no, actually there are carbon monoxide adsorbed, but this oxygen atom, there are carbon monoxide adsorbed, but they do not react with the adsorbed oxygen species. The carbon monoxide in the gas phase actually reacts with the adsorbed oxygen species to give you CO2. So one mechanism, so this is mechanism 1 and this is mechanism 2, and this one is known as Langmuir or Langmuir-Hinzelwood mechanism, and this is known as Elie-Riedel mechanism. So the both mechanisms says there is an initial step. See, oxygen has to be adsorbed on the surface, and the O double bond O has to be broken, otherwise this reaction won't proceed. Now the question is, I have on the surface I have oxygen attached. I also have carbon monoxide attached. I'm just drawing it like this. Now the question is, there are also oxygen molecules here, and there are also carbon monoxide molecules here. And these are oxygen atoms, by the way, so I should draw it like this. So this is O2, this is carbon monoxide. Now the question is the reaction between this carbon monoxide and the attached already adsorbed oxygen atom, or it is between two surface species. So it can happen that the molecules get adsorbed and get dissociated. So there are oxygen atoms and there are carbon monoxide atoms, and on the surface they are now working, they are now reacting. So it's a collision on a surface, which means it's a two-dimensional collision. So you can actually model it by in a very interesting way using two-dimensional distribution of Maxwell-Boltzmann distribution, but we'll not discuss it right now, because we'll discuss it at the very end, how to use Maxwell-Boltzmann distribution to discuss the reaction rates or get an expression for the rate of the reaction. Now the first model we'll try to solve, and you see that it is very easy to solve, because I'll give you a hint how to solve it. So you have to have basically the two sides here. So you can say that there are one type of site where carbon monoxide is attaching, or suppose that there are these sites are same, but you say that this is basically the fraction of sites, fraction of surface sites basically, which are occupied by carbon monoxide. And then you can also say that, okay, there are also fraction of oxygen which are of sites occupied by O atoms. And so the fractions which are fractions of sites unoccupied will be nothing but 1 minus theta CO minus theta O. So that is very important here. So you have same type of site, and both model, when you develop it, you have to consider this. Now it is very easy. So you just calculate what are the or your rate of the reaction here will be nothing but for the first mechanism. For mechanism 1, the rate of the reaction will be nothing but K3 into CO adsorbed. You may write it like this, CO ADS times you have oxygen atom adsorbed. Now you have to find these two numbers from the reaction from the first two equilibrium, and this is as simple as that. And we have already described it, how to do it. So we can quickly do it. So it is basically K3. Now if you go back, you will see that here what you are seeing here is that theta is basically we need the pressure actually. So so again, rate of forward reaction and rate of reverse reaction will be same. And for the first equilibrium, you can write it that the rate of adsorption, which is 1 minus theta CO minus theta O times carbon monoxide in gas, that's concentration, will be equal to the rate of desorption. Now desorption means actually it is only theta CO, and then there will be some rate constants. So it is K1. I'm calling this as step 1, say. This is step 2. This is step 3. This is also step 3. So step 3 differs for these two mechanisms. I'm calling this as K1. This is as K minus 1. This is K2. This is as K minus 2. So this will be K minus 1 then. And then we'll just take the ratio. All we need is basically the adsorbed species concentration, or the here actually you cannot write the concentration, you have to write in terms of the fraction. Just remember that, because it is the CO adsorbed will be nothing but proportional to theta CO. So that is equivalent to saying the CO adsorbed. And similarly for oxygen, you can write it, it's a dissociative oxygen. So remember that that forward rate will be nothing but K2 into 1 minus theta CO minus theta O into O2. And the reverse rate, now you have in the stoichiometry, it is 2O. So it will be if you ask this question just from your kinetics knowledge, so it will be just whatever is there, oxygen theta for oxygen, that will be squared, because it's 2 factor is there. So we'll have basically K minus 2 into theta O, and that will be basically squared. And then you can actually solve it for this thing and this thing. So all you can actually easily see it. So if I just bring it here and call it as equilibrium constant, that theta oxygen, that part will involve actually a square root. So ultimately if you solve it, so you will get very interesting equations. I'm just writing the final solution. For the mechanism 1, you will get the rate of the reaction, which is K3 into CO adsorbed into O adsorbed. That will be nothing but, if I write it in terms of partial pressure, I could have written it in terms of B and P also. So it will be nothing but K3. K3 will always be there. And I'll have BCO and pressure of carbon monoxide multiplied by BO2 and pressure of O2 to the power half. Because you can see that when I solve for theta O, on the left hand side, all these things has to be, I have to take the square root. That's why the square root is coming. And divided by, I'll have basically 1 plus BCO, PCO, and that plus BO2 to the power half and PO2 to the power half. And for the second mechanism, you will have B is equal to K3 times for the other mechanism, for this first mechanism there will be a square. Yeah, you can actually work it out, and it will be K3 into BCO and BO2, or maybe we can write the pressure term together, BCO and BO2 PO2. This will be always half, divided by, I'll have 1 plus BO2 to the power half, PO2 to the power half, and plus BCO and PCO. So we'll see that we saw that there is a square term in the denominator. So if we plot it now, that how the theta versus P follows, if it follows the mechanism 1, then you just think about it at a low pressure. Say I'm plotting it as a partial pressure of carbon monoxide, because if you change the partial pressure of oxygen, that don't matter, because the oxygen part is same in both cases, and because it is oxygen adsorbed species that actually reacts. But for carbon monoxide perspective, it is very different whether it is carbon monoxide adsorbed or whether it is the carbon monoxide which is in the gas phase. Now the question is, if I do that, then I'll see PCO, and then if you ask this question, what is the rate of the reaction or the fraction, or we can actually plot the rate of the reaction here. So at a very low pressure of PCO, think about it, what will happen, then I can ignore this part, PCO, and if we ignore it, then I'll have 1 plus BO2 and PO2, and in the numerator you can see that it will be linearly proportional to PCO, so it will be something like that. In both cases it will be true, but in the very high pressure limit, what will happen is that now you can actually ignore this part. I mean, this will be nothing but only this part. So you can think that this part will be so high. So mechanism 2 I am also plotting together. So for low pressure regime it will be similar, it is just linearly proportional at a very low pressure. And then because this term is very small and you can neglect it compared to other terms, so then with respect to PCO it will be linear. But in the very high pressure limit, when I have this term dominating PCO over the other two terms, then in the Langmuir case, remember there is a square, so it will go inversely at as PCO, because there is a PCO here, there is a PCO square here, so it will be 1 over PCO. And in this case it will just perfectly cancel, so it will be just saturated. So this will show a behavior like this, Ellie-Riedel. But Langmuir case, in the very high pressure limit, it will be 1 over PCO, so the overall curve will look like something like this. So you will see that these two mechanisms actually predict very two different behavior of the reaction rate versus the partial pressure of one component, which is the carbon monoxide. And then experimentally it was found that it actually follows this curve, which means this mechanism which Langmuir and Hinshelwood proposed is the correct mechanism and not the other mechanism which Ellie and Rydell proposed. But Ellie and Rydell mechanism holds for other reactions, not for this particular reaction, carbon monoxide and oxygen. So the reaction proceeds via between in the rate determining step. It actually the step actually involves collisions or reactions between two adsorbed species. It is adsorbed oxygen with adsorbed carbon monoxide, whereas the Ellie Rydell said that it happens between one adsorbed species, which is carbon oxygen atom, and the other species is in the gas phase. You can have a carbon monoxide adsorbed, but that doesn't react with oxygen according to Ellie Rydell mechanism. The carbon monoxide in the gas actually comes and hits the oxygen atom adsorbed, and then it forms carbon dioxide. So in this particular example, it follows the Langmuir-Hinshelwood mechanism. So we'll stop our discussion on the mechanism of reaction here. So this part is slightly different than the earlier parts in the sense that it is a heterogeneous thing that we discussed, and it involves a surface. Just like we had a small discussion on surface chemistry after chapter at the end of as a part of the lecture or module 9, where we discussed first the application of thermodynamics. So one was equilibrium electrochemistry, and the part 2 was basically the surface chemistry. In that same way, we just kept the surface chemistry towards end, so that it is slightly different from the others, because usually we talk about everything as a bulk phase, and all the reaction kinetics or the thermodynamics we mostly have discussed for the bulk phase. And this is one unique example how surface catalysis helps and surface catalysis works. Nevertheless, surface catalysis is very, very important, particularly this heterogeneous catalysis. And for heterogeneous catalysis, we all survive, because if the ammonia production was not demonstrated by Haber, we would have died by now because of crisis of food, because ammonia is a very, very important constituent for fertilizers. All right, so we'll just conclude our discussion on the mechanism here, and next we'll start the reaction dynamics. Thank you.